Okay, നമുക്കിന്ന് ആംഗുലാർ മൊമെൻറ്റം ആൻഡ് ടോർക്ക് നോക്കാം. നമുക്ക് angular momentum of a particle is defined as the moment of its linear momentum. നമ്മൾ ഓൾറെഡി പ്ലസ് ടുവിൽ പഠിച്ചിട്ടുണ്ടാവും ആംഗുലാർ മൊമെൻറ്റം എന്നുള്ളത്. We can define J as equal to R cross P. P is a linear momentum. So R cross P, R cross P is the moment of the linear momentum, that is J, angular momentum. Okay, so P is linear momentum, P is R cross V. So we can write, P is equal to m mass into velocity. So we can write m is constant. You can take it out. So we can write R cross V, m into R cross V. So J is equal to R cross P equal to m into R cross V. That is the angular momentum. Where R is the vector distance of the particle from that point, and P is equal to mv is the momentum in an inertial frame in which the point is stationary. Okay, the unit is mass kilogram, velocity meter per second, then R is meter, so meter square by second, by second, or joule second. Okay, for circular motion we know that the velocity is m into v, velocity is omega r. So we can write, and we know that R cross V is perpendicular, both are perpendicular, so we can write RV, say MRV, then instead of V we write omega R, so we can write MR square omega. So the magnitude is MR square omega or MVR. Then if we differentiate J with respect to t, dj by dt, we can write d by dt R cross P. Then from vector differential we can write dr by dt cross P plus R cross dp by dt, where dr by dt cross P becomes dr by dt is velocity, so we can write v cross P. P is mv, so m is constant, it becomes v cross v, then this term becomes 0. Then finally we have dj by dt equal to R cross dp by dt. dp by dt is rate of change of momentum, that is force, so we can write dj by dt is R cross f. So where dj by dt is R cross f. R cross f, f is torque. So R cross the torque or moment of force, so we can write T, torque is equal to dj by dt is equal to R cross f. അപ്പോൾ നിങ്ങൾ ശ്രദ്ധിക്കുക, സ്റ്റെപ്പുകൾ ഓർത്തിരിക്കുക. ജെയിൽ നിന്ന് നമ്മൾ ടോർക്കിലേക്ക് എത്തി. ഓക്കെ, ടോർക്ക് ടി ഈക്വൽ ടു ഡി ജെ ബൈ ഡി ടി ഈക്വൽ ടു ആർ ക്രോസ് എഫ്. സോ ദ ടോർക്ക് ഈസ് ഈക്വൽ ടു ദ റേറ്റ് ഓഫ് ചേഞ്ച് ഓഫ് ആംഗുലർ മൊമെൻറ്റം. ഓക്കെ, യൂണിറ്റ് ഈസ് ന്യൂട്ടൺ മീറ്റർ. Then if there are many number of particles moving independently or attached to one another in the form of a rigid body, then the angular momentum of the system about any point is defined as the vector sum of angular momenta of separate particles about the same point. So the angular momentum J equal to J1 plus J2 plus and so on. Then we can substitute J1 as R1 cross M1 V1 and so on. And finally we can write torque T equal to summation Rn cross Fn. Okay, നമ്മൾ നേരത്തെ ചെയ്ത അതേ സ്റ്റെപ്പിനെ നമ്മൾ ഇവിടെ ഫോളോ ചെയ്യേണ്ടത്. Hence the rate of change of angular momentum of the system about any point is the sum of the torques about that point of all the external forces acting on the system. In a free system left to to itself, the external torque is 0, or simply if the external torque is 0, then we can write dj by dt equal to 0. That means j is constant, angular momentum is constant. Or if the angular momentum is constant, torque is 0, then we can write, if angular momentum j is constant, then dj by dt equal to 0. That is j is constant, that is j equal to j1 plus. For individual particles we can write j1 plus j2 plus and so on, which is constant. That is the total angular momentum of a system of particles is constant if the resultant external torque acting on the system is 0. And if this is the constant of motion, this is the constant of motion, that is the conservation of angular momentum. Okay, but in the absence of external torque, the total angular momentum of the system remains constant. Then the angular momentum and angular momentum about center of mass JCM we can write as we can write as J equal to R cross MV plus summation RNC cross MN VNC. ഇതെങ്ങനെ കിട്ടിയെന്ന് വെച്ച് കഴിഞ്ഞാൽ ഈ സ്റ്റെപ്പ് നിങ്ങൾ ശ്രദ്ധിക്കുക. If capital R and V are the position vector and velocity of the center of the mass, and RNC and VNC those of a particle of mass Mn relative to the center of mass, then the position vector and velocity of the particle with respect to the reference point are given by Rn equal to R plus Rnc. Okay, this R is the capital R is the position vector of the center of mass. Rnc is the position vector relative to the center of mass. Okay, so Rn is the position vector with respect to the reference point. Then Rn is equal to R plus Rnc, Vn equal to V plus Vnc. So the total angular momentum we can write J equal to summation Mn into this R plus Rnc, that is Rn cross Vn. Okay, instead of Rn we write R plus Rnc, instead of Vn we write V plus Vnc. Okay, then it is like A plus B cross C plus D. So we can write R cross V plus R cross Vnc plus Rnc cross V plus Rnc cross Vnc. The Mn is the summation is here. So we will get this statement. And RNC we can write Rn minus R, and VNC we can write Vn minus V. Okay, and from MNC RNC we can write MnRn minus MnR, and MNC RNC, if we substitute the summation, it becomes summation MnRn minus summation Mn capital R. Then summation M is total mass M. This is summation M, and M1 plus M2 plus M3, that is capital M, then is R. Then this term becomes summation MnR. From the center of mass we can write M1R1 plus M2R2 plus as summation Mnrn. So this becomes capital M capital R. So this becomes 0. That is summation Mnrnc equal to 0. Similarly, you can also prove that summation Mnvnc equal to 0. ഇതേ സ്റ്റെപ്പിനെ നിങ്ങൾ Rnന് പകരം നിങ്ങൾ Vn സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് കഴിഞ്ഞാൽ നമുക്ക് summation mn vn മൈനസ് എം വി നമുക്ക് എഴുതാൻ പറ്റും. അത് ഇതിനെ നമ്മൾ കൂട്ടി സമ്മേഷൻ ചെയ്ത് കഴിഞ്ഞാൽ എം വി മൈനസ് എം വി എന്ന് കിട്ടും. അത് ക്യാൻസലായി. അപ്പോൾ ഈ ടേം രണ്ട് ടേം നമുക്ക് ക്യാൻസലായി 0 ആയി. സോ റിമൈനിങ് ടേംസ് ആർ ആർ ക്രോസ് വി സമ്മേഷൻ എം എൻ ആർ ക്രോസ് വി. സമ്മേഷൻ എം എന്ന് പറയുമ്പോൾ ക്യാപിറ്റൽ എം ടോട്ടൽ മാസ്. അപ്പോൾ ആർ ക്രോസ് എം വി നമുക്ക് എഴുതാം പ്ലസ് ലാസ്റ്റ് ടേം എം എൻ ആർ എൻ സി ക്രോസ് വി എൻ സി. ഇതിനെ നമുക്ക് സമ്മേഷൻ ആർ എൻ സി ക്രോസ് എം എൻ വി എൻ സി എന്ന് എഴുതാൻ പറ്റും. Here this term represents the angular momentum of the system over the center of mass, that is JCM, and mv, that is mass into velocity, is the linear momentum. We can write p, then the total linear, that is the total linear momentum. The quantity r cross p or rmv is the angular momentum of the center of mass at the reference point. Thus total angular momentum J is JCM, that is the angular momentum with respect to the center of mass plus R cross P. Okay. Then motion under central force. A central force acting on a particle depends only upon the magnitude of its distance from fixed point. If R is the instantaneous position vector of the particle relative to the fixed center, then the central force is also represented as F is equal to F of R into unit vector R. F of R is a scalar function of distance R, and in the circular motion the torque is 0. If the torque is 0, we can write T equal to dJ by dt, which is equal to 0. We have already seen that J is constant. That is R cross mv is constant. That is the angular momentum of a particle moving under central force is conserved. Okay. dJ by dt is, if dJ by dt equal to 0, that is the torque is 0, that is J is a constant of the motion, then J is conserved. This means that the path of a particle in the influence of a central force lies in a plane. Then now we assume that the area of this triangle, that is the delta s, is area delta s subtracted by the radius vector in this time. And we know that the area of a triangle is half bh, and using that statement we can write delta is equal to half r cross delta r cross delta r, and the area is subject delta t, so we can differentiate delta s with delta t. Therefore the area subject delta t time, and therefore we can write delta s by dt equal to half r cross delta r by delta t. Delta r by delta t is velocity, so we can write it becomes delta ds by dt equal to half r cross v, that is r cross v. And from this equation we know that J equal to r cross mv, that is m is constant, so we call r cross v equal to J by m. Then substitute here r cross v J by m, so ds by dt equal to J by 2m. This expression gives the aerial velocity of the particle. J is a constant for the particle moving under central force, that is the aerial velocity remains constant when the particle moves in the influence of a central force. For example, നമുക്ക് satellite motion നോക്കാം, planetary or satellite motion. We know that the planets move in elliptical orbits about the sun at a focus. The gravitational force on the planet is directed towards the center of the sun. In other words, this force is central force. Consequently, the angular momentum of the planet will be constant, and so the orbit of motion will be plane. For planetary motion, the constancy of j means that the aerial velocity ds by dt equal to j by 2m is constant. Thus, the rate of sweeping out of the area by a radial vector from Sun to the planet is a constant. This is known as Kepler's second law of planetary motion. You can also apply this to the artificial satellites also. In planetary motion, the conservation of angular momentum across mv, the planet must move faster at the point of closest approach to the Sun than at the farthest point. The reason lies in the fact that at this point the angular momentum is mvr, and for its constancy the shorter r is associated with larger v. If r1 r2 are the distance of closest and farthest point of the planet respectively, and v1 v2 are the corresponding velocities, then mv1 r1 equal to m2 v m mv2 r2, or v1 r1 equal to v2 r2. Okay. Okay, thank you.